Hello, everyone. Hopefully you can hear me well. We'll get started here in just a minute or so, too. All right, can everyone hear me and see my presentation? Give me one moment. That's right, I have to do that first. Yes, excellent. All right, thank you everybody for joining. My name is Will Steinberger, and today I'm going to be presenting an introduction to scatter-based imaging and fundamentals of imaging. So with that, just starting off, as always, if you have any questions, please feel free to enter them into the chat and we'll get to them at the end of the presentation. So let's jump right off with some motivation for this work. And there we go, some motivation for this work, specifically for imaging systems and why we would want an imaging system versus, let's say, a standard detection system. Most detectors that you'll find that are deployed or used currently are just either counting detectors or spectrometers, meaning that they focus on looking at count rates as a function of time relative to some background that they detect or have been calibrated to, for instance. Such that you're looking for a change in how many particles you are detecting. You can also have systems that are spectroscopic, such that you're looking for specific lines, specific photo peaks, or specific gamma ray interactions, such that you are aware of the presence of a source. You can then look at how those sources change as a function of distance or moving, the intensity of those peaks, or your count rate to try to localize a source with that system. With an imaging system, theoretically, you can either carry the system around or have it in a designated spot, and based off of kinematics of interactions with said imaging systems, it can give you some confidence or some probability of where a given source is located, such that with just one system, you don't have to really move it around or anything like that, and you can be able to localize a source of radiation. And this can be very useful in two scenarios that I have here: a search and emergency response. This one specifically where imaging can be very useful to begin to localize sources of radiation. As I said, for counting detectors, for instance, you have to be able to sweep a large area, or you follow a 1/r squared, because as you get further away from a source, the radiation intensity drops. As you move closer, it gets much, much stronger. However, that's very subject to background. And if there's any direct shielding or indirect shielding, things of that nature that can change and fluctuate that surrounding environment, versus imaging systems are not necessarily as sensitive to that and can still localize on sources. Another application for imaging systems that is of interest is for verification. So it was a case study actually at Oak Ridge National Laboratory where they were trying to verify a plutonium beryllium source. And they were trying to do this via spectroscopy, looking at the americium emitted from the source. And they were having issues because they were looking at count rates, specifically using a high purity germanium detector. And because the count rates were so sensitive to the position of the detector, they had difficulties validating if they were actually in line with the source, what kind of source, things of that nature. They could theoretically use an imaging source, and specifically a neutron imaging source would work very well, such that you can image the source and you constantly have a localization of that given source so that you know that it's always there. And for just an example for a system, you see here on the right we have developed at the University of Michigan the dual particle imager. This was a two-plane system that was able to detect and image both neutrons and gamma rays with this system. And for this lecture, I'm going to predominantly focus, or I'm going to introduce neutron imaging for how we go about actually doing cone projection and what that means for a scattered system. And then we'll end with a little bit of gamma ray imaging. So with that, let's jump right into it. So neutron imaging, how do we go about neutron imaging? Let's say we have a very simplistic system, just two detectors, and we have our source of neutrons. We have some neutron come in, scatter in our first detector. This gives us some information. It gives us an energy deposited, it gives us a location, and it gives us a position, or it also gives us a start time. We can then see that neutron go and scatter into a different detector. And from that, again, we get energy information, position information, and then timing information. So because neutrons do not move relativistically, well, neutrons less than 10 MeV, which is the majority of neutrons that we're going to be looking at in fast neutron and for fast neutrons, do not move relativistically, such that we can figure out the kinetic energy of the neutron after that first scatter interaction based off of the time of flight. So we can figure out the velocity of the neutron, which is just the distance over time, and then figure out the time of flight or the kinetic energy of the neutron. If we then know the kinetic energy of the neutron, we can sum that with the initial energy deposition, and then we can know the incident energy of the neutron. So the systems that are scatter-based neutron imaging systems are spectrometers. We can then figure out the scattering angle relative to what we'll call the cone axis here, theta, based off of the equation you can see in the bottom right, where cosine squared of theta is equal to the time of flight energy over the incident energy. And we can then project a probability distribution of where that neutron originated from. And this is called a cone projection. And what is going to follow is how do we actually go about solving for these cone projections to determine this probability distribution. So to begin, let me check hold on one moment, sorry. Okay. Sorry about that. So cone projections on a pixelated sphere. So generally, this application will show a cone projection along a sphere. Cone projections can be done along a flat plane. There are even methods that you can see the cone projection that you can apply this in 3D space as well. This is just one methodology that's commonly used. So a sphere center, so what we do is we project a sphere around our system. So let's say you have a detector system that has a point 000 in real space at the center of the system, and you have a pixelated sphere around that system. We can take this pixelated sphere around the system and break it up into 2 dimensions. So we look at just the altitude angle and the azimuthal angle, where the altitude goes from 0 to pi, and then of course the azimuthal angle goes from 0 to 2 pi. We can then solve for these positions in space and figure out where our cone projection interacts with this sphere. And what do I mean by that? So let's break down some of the mathematics here. So here, let's say I have our altitude angle and our azimuthal angle. You can think of this as a 2D matrix. We now want to break this into X, Y, and Z space. So position space instead of angles around our system. So we're going to break through and break down these equations real quick. So the first one is just, these are the X, Y, and Z positions of any given point in a sphere given some azimuthal angle theta and some altitude angle phi, multiplied by r, which is the radius of our sphere. Pardon me, which gives us a position of a pixel in space. We can then, you can see x sub b here, we can then put each one of these positions as a given point in space that has some x, y, and z. We can then figure out the vector or the, pardon me, next step is to look at what is the lever arm. This is the vector between our first interaction and our second interaction in the 2 detectors. We then look at the angle between every given position in our sphere. So this is the x sub b, which is the x, y, and z for each one of these positions in the sphere, minus our first interaction position. So you can see that as the vector going out from where the initial interaction happened and any given point on this pixelated sphere. And we can figure out the angle between that vector and our lever arm here, where the lever arm is the angle between these 2 points, such that what we can then do is compare that angle with any given angle that we find, with any angle that we find via the neutron imaging. So for reference, what we're doing is we're comparing this angle that we found, which is the time of flight over the total energy of the incident neutron, with the angle between our lever arm and any given angle on the which is the angle between the vector of our lever arm and any given point in our pixelated sphere. And we simply throw those into a cone projection, and if we are assuming Gaussian broadening, you can see that this is the main portion, the exponential, for a Gaussian distribution, which you can think of this in just a simple Gaussian distribution where you have some mean and then you have some space over that mean. So in this case, the alpha, which is the angle based off of the kinematics of the scattering for our system, is the mean of our distribution. And then we have the total space for our image or for our distribution, which is beta sub b. And then, of course, we have some uncertainty in both alpha and beta, which we propagate, which gives the projections some width, such that they aren't just single pixel lines where it would just be the scattering angle that we solve for around our lever arm or our vector there. So now that we've gone over this, how do we actually apply this? What does this actually mean for imaging capabilities? So this all seems very complicated, but let's just break it down into a simple problem here, where we have some cone projection where we have detector 1 and detector 2, just like we saw, and we have their locations in space. So detector 1 is in the positive x space, detector 2 is in the negative x space, 5 units forward, negative 5 units back, and let's assume that we get an alpha cosine squared theta of 0.5. In this case, you could assume that's a time of flight energy of 0.5 and then an incident neutron energy of 1 MeV. And if we assume just a 10% uncertainty on our alpha, we can run it through those equations, and in that distribution we can see that we get a cone projection here, where this is centered at 0, 0, as we expect right down, and then has a 45-degree angle around it. Now this looks elliptical because of the space that we are displaying it in and how we're going about displaying this. This is from negative 180 to positive 180 degrees, and from negative 90 to 90 degrees, which covers that full spherical space, or that full pixelated sphere, but looks distorted given how we're displaying it here. And we can check by just switching out our positions for our detectors whether or not this is truly working, such that, let's say we're just doing this in the y direction, where we have the same input parameters. And if we do that, we can see that we've shifted our cone projection to the right by 90 degrees, as we expect based off of these reactions. So now that we can do this for a single event, we want to do this for many events, because it doesn't necessarily help us that we see, a source can be in any one of these positions, such that we want to add many of these cone projections together and then be able to localize a source by summing all of those projections. And that ends up looking something like this. where we normalize our cone projections and then sum them to generate what is called a simple back projection image. And you can see here in this data set, we get just about 1,100 events, and that begins to really start to localize our source and give you an idea of where the source is in this azimuthal and altitude space. In this case, it's directly centered in front of the system, and you can see the hottest spot for that centers directly in front of the system. So simple back projection images. How do we actually understand these? What influences them? This is a very important question for being able to design and then understand an imaging system. And for that, we have to go back to our equations. So the first one is the angle between the lever arm and any given pixel. Where this one is majority the lever arm, such that if you are limited in the number of lever arms, you can only generate angles relative to that lever arm. And because there's only so many possible scattering angles for, in this case, neutrons, depending on the geometry of your system to interact with, this can be a very limiting factor in that you can only project interactions at that one spot. If you have a continuous position detector, then that helps negate this effect, but we'll show that in just a little bit. So this lever arm and how many of these lever arms that are in a system greatly impacts the simple back projection images. Of course, the scattering angles also impact this. Whether or not your system allows for lower angles or higher angles, or is it more in between angles, also greatly impacts your simple back projection image. And then finally, on the cone projection, and specifically the uncertainty associated with the cone projection, where if we have very, very high uncertainty in our time of flight, or in our initial energy, that can significantly broaden it. If we have very high position uncertainty, especially in the where we're projecting our vectors, that can also have a significant impact on the system. And we're going to break all of these down and show how each one of these impacts simple back projection imaging. So the first thing that we're going to do is we're going to show a little bit more of a simulated interaction position. So what I've gone ahead and done is generate cone projections around a centered point. So you can think of each one of these here as a initial detection location, where I have a point back here such that I have an angle going around a point centered behind this circle, such that I have an angle going through each one of these points into my projection. And what that basically means is that we are getting cone projections that go around a given point, and this centered point is 0, 0, 0. So you can see here, this point refers to this cone projection. If we look at the bottom point, it refers to the bottom cone projection here. And then if we have one on the left, it goes to that cone projection. This is our distribution, effectively, of lever arms for this given position, such that we have one point centered here that we have some scattering angle around, one point centered here with some scattering angle around, one point centered here with some scattering angle around, and then these all have some associated broadening, which is giving us the distribution effect that we're seeing. So now that we've gone over that, we can also look at relative uncertainty. And this is quite interesting in that you can see here where we have a 10% relative uncertainty, a 50% relative uncertainty, and then 100% relative uncertainty, where this distribution is getting relatively broader each time. And we can also look at, because we are normalizing each cone projection, the intensity of these distributions is also dropping. And that's very important because we don't necessarily want to weight our images by events that have greater relative uncertainty. So by normalizing our image, by normalizing these cone projections before summing them into simple back projection images, we get around that effect where more certain events give us more information than less certain events. And what we're going to do now is begin to build a simple back projection image based off of the simulated data. So what you can see here is that what we're going to do is go through each one of these configurations and then sum each one of them, such that for each one of these points in this distribution going around this point, we're going to vary it from 10% relative uncertainty to 100% relative uncertainty in 5% increments. And we're going to sum that for the entire system. We're also going to change scattering angles, and we're going to see how scattering angles impact our system. And you can see that here. So in the top right, where we have a scattering angle of 25 degrees. In this case, our lever arm has to point to that 25-degree azimuthal position such that our cone projection can intersect with our source at 0, 0. In this case, our simulated source and simulated analysis. In this case, 45 degrees, we of course have to shift that, and then we get our interaction, and then this 60 degrees. And we can see, very interestingly, as we're increasing the angle here, we're getting this effect that these cone projections are, even though these are all the same relative uncertainty, we're actually getting much sharper cone projections with them. So something interesting of note there. And we are varying our scattering angles from 10 to 170 degrees. At each one of these then, for each one of these angles, for each one of the points going around them, we will then simulate all of our angles from 10 to 170 degrees, and then with relative uncertainties from 10 to 100%. And when we do that, we get something that looks like this. And this is theoretically a target simple back projection image. This is what we really want, where we have a very nice distribution, where we have a very clear hotspot and a very symmetric system, and a very symmetric, what we call a point spread function here. Yes. So now we can see if we vary any one of these inputs, for instance, if we vary the lever arm distribution, or if we vary our relative uncertainty, or if we vary our number of scattering angles, how does that impact this image? So the first one that I want to talk about is broadening, because broadening seems like it would absolutely impact these images significantly, such that if we take a system that has upwards of 100% uncertainty, and if we reduce that by some factor, won't that give us a much, much better image? And what was interesting about this analysis is not so much. So our initial image, we had an uncertainty range from 10% to 100% relative uncertainty in 10% increments. To keep the statistics constant for each one of these images, I altered the uncertainty range and did it just in smaller increments. So a 10% uncertainty to 50% uncertainty, and then a 7.5% to 27.5 uncertainty. And what we see is that initially dropping our average uncertainty down from a range of 10% to 100%, to 10% to 50%, we actually don't see that big of a change in our simple back projection image. In fact, if we look at the full width at half maximum, so just taking a slice here in both the azimuthal and altitude, we actually see a slight increase, even though we had a decrease in our relative uncertainties. And I think that's because of how the higher uncertainty events in this case, in the above case, actually have less contribution to the net image than the lower uncertainty events, whereas that is not as large of an effect for this image. But if we drop the uncertainty down even more, in this case down to a maximum of 27.5%, we do then see that this begins to reduce our image resolution. And we can also see, because of how we're going about this simulation and cone projection process, we do see different striations in all of these images. And that's because we're doing this all very discreetly and very well and precisely known, such that we're getting these artifacts in the images. And we'll actually amplify those artifacts in just a minute and discuss how those impact our system response. But we can see that broadening absolutely reduces our image resolution, such that we can, if we reduce our uncertainty, of course, then that improves our image resolution such that we can more accurately know where a given source is. We can also look at the scattering angle of if we reduce the range of scattering angles for our system, how does that impact everything? So in this case, we have our base image here, scattering angles from 10 to 170 degrees. So all the way up to very low angle scatters to very high angle scatters. And if we begin to truncate that closer to 90-degree scatters, we can see that we also get significant improvement in our image resolution in this case, where we're cutting our full width at half max in our initial cut by roughly 10 degrees, and then we still get some improvement in the azimuthal and altitude by even limiting the scattering angles even more. So when looking at a system, the scattering angles are very important and definitely contribute to the image resolution. So both of these things, both the broadening and scattering angle, if you want a system with a given image resolution or a given capability, these are definite considerations that need to be taken into account in that design. Now, of course, the trade-off with these things generally always in the real world is efficiency, in that if you are cutting out a significant portion of your scattering angles or of your uncertain events to be able to obtain better image resolution, odds are you're throwing out a significant portion of events, which means you have less statistics in the image. And while we're not going to cover statistics in the images in this presentation, that is something to be of interest. Now, the last thing I want to talk about is what was the lever arm distribution, because this is where it can completely change the shape of the given simple back projection image. So by lever arm distribution for all of these, is this angle or is this vector between the first interaction and our second interaction in the first detector and our second detector. If I normalize this vector and plot it in a 3D space, you can see it looks like this for this image, such that we have all of these low angle scatters that have all of these lever arms very close to the 0, 0 point. And then as we go farther and farther out for the angles, you can see that they get farther and farther away from that 0, 0 point, which is what we expect and shows that we are projecting things correctly. But you can see that this is a very symmetric distribution around this point. So the question becomes is, what happens when we limit that symmetry around our system? And we get some very interesting effects. So the first one here, you can see we have 4 lever arms, such that we are only projecting events in 4 directions. So all of our cone projections are along the azimuthal and altitude along 0, 0. And if we do that, you can see we get a very distorted image in that we do not get something that is, while it is symmetric, is not in the circular or it's not a Gaussian distribution, but it is not a smooth distribution that we're seeing in both the azimuthal and altitude space. We're getting some very interesting artifacting around that. Whereas as we increase the number of lever arms to, I believe, 20 and I believe 30 here, we see this effect go away and we obtain a more symmetric image as we're increasing this number of lever arms. And of course, if we have the lever arm distributions completely non-symmetric, we can really begin to alter the shape of our distribution. So on the left here is our symmetric distribution where it's all around our 0, 0 point. And then I said, what happens if we just don't project anything above or below? We have no distributions there. And we get this fun shape such that we are only projecting things along angles around the azimuthal and not in the altitude above the source. And we can see we get this elongation effect where we actually have a smaller full width at half max in the azimuthal axis or in the azimuthal direction, but a larger one in the altitude direction. And you can think of that because here we have all the cone projections overlapping, 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 and they're doing so in a symmetric fashion such that if such that it normalizes out any effect of the cone projections in areas away from the source. However, here in this distribution, because we only have lever arms going in effect in this area in the azimuthal space, when we have a cone projection around here, we don't have anything above the system to alter this area and to show and to negate that impact, such that when we add up all the cone projections here, all of them begin to intersect for this location, and because we're doing it symmetrically, it's along both sides, but we get this elongation effect. And we have them all intersect so that this width is largely due to just the broadening from those cone projections in this area. So lever arm distribution is very important. And of course, this is all simulation. But this absolutely has a real world impact and real world effects when performing experiments or developing imaging systems. So I'm going to take you through one of those systems very quickly here. And that is what we have deemed our mini cube imager. And this is to show that you don't really need a huge space. You don't really need a very complex system to develop an imager. In this case, we use 2 cubes of LISO, Teflon tape, PTFE, that you can see here in these positions, and 5 steel beam cubes wrapped in Teflon, 1, 2, 3, 4, 5, and you can see they are all coupled to a silicon photomultiplier array. And in this case, we're using a combination of steel beam, which is an organic scintillator, and LISO, which is an inorganic scintillator, to perform Compton imaging. In this case, we're looking at double scatter events where we have a scatter in, and here I just have a layout of the system, scattering in any of the steel beam cubes. Because it's an organic scintillator, we know that the dominant scattering mechanism for gamma rays is going to be Compton scattering. So we look for a Compton scattering event in our steel beam cubes, and then we look for a photoelectric absorption in our LISO cubes. And of course, LISO is very high density and has a high Z, such that we know if we get, such that when we look at a distribution, we can pick out where we have Compton scattering in our first interaction, photoelectric absorption in our second interaction, and then we can back project those events. Now, back projection for Compton imaging is all the same in formulation with the exception of the cosine theta of the angle. In this case, it is equal to this equation right here, where E gamma is the interaction, where E gamma is the incident energy of the gamma ray, and E gamma prime is the energy deposition in the second interaction. And then MEC squared is just the mass of an electron. And this can be put into the exact same equations that we initially started off with, and we can do the same type of back projection with this system. Something to note generally with Compton imagers that makes this more difficult, though, is that neutrons move much, much slower than the speed of light. A 1 MeV neutron moves at roughly 1 centimeter per nanosecond. Generally, these systems have on the order of 200 picosecond time resolution, which means that we can see, if we have a flight path of 1 centimeter, we can see a neutron scatter in one detector and then scatter in another detector. Gamma rays move at 30 centimeters per nanosecond. So we're not going to be able to resolve gamma ray interactions. So for this system, that's the main reason we use the combination of cubes, of steel beam cubes and LISO, such that if we look at a coincident spectrum, so if we only look at coincident events between the steel beam cubes and the LISO, and we sum the energies of those two interactions, we can get that distribution seen in blue here, which is from a cesium-137 source. Cesium-137 emits a 662 keV gamma ray, and you can see that we have a photo peak where that gamma ray, where we get that full energy deposition of that gamma ray. And if we gate on those events such that we only back project those events, you can see we obtain the following simple back projection image. And our source was placed at 0, 0 directly in front of our system, and we can see that it is able to isolate that or localize that source very well, with the caveat that we're getting these two wings around our image. And of course, we can explain these wings based off of our lever arm distribution. So if we look at our system here, we can see that for forward scattering events between our still beam cubes and our LISO, we only have two angles. And because of the symmetry between these two sets, so correction, we do have a third angle where this still beam cube can have a forward scattering event that interacts with this LISO, but two dominant scattering angles because because the scattering also goes with with the solid angle between scattering locations, such that it's more likely for interactions to occur between closer detectors in this case. So we have two dominant scattering angles between these two with a minor third, and then we also allow for backscatter events. However, backscatter events tend to be less broad, or tend to have not as high of an effect in this system. And what that ends up giving us is these two wings around our system, which each one of these wings is centered around that angle between the still beam cubes and the LISO. So this is an actual application where this is a very small compact system and is not highly complicated in that the still beam, you just need some organic scintillators, some inorganic scintillator, and coupled to a silicon photomultiplier array. Now, something of interest that we saw with this is you see that we get some cone projections that don't seem to align with our source at all. And this was an interesting thing to look into, that this will be the last thing we touch on for today, which is where do those come from? And something to remember when looking at inorganic scintillators is that some of them do have internal radioactivity, such that LISO is one of those scintillators. Even though it has a great density and Z value for gamma ray detection efficiency, it also is internally radioactive, such that it has an internal background, and that background can trigger with background coincidence with the still beam, and you can actually get a coincident spectrum. So in this case, we moved our source back another 30 centimeters, which is just reducing the intensity of our source. And in this case, instead of showing the gate on the photo peak, I showed the contribution from the background radiation to our system. And you can see in this configuration, our photo peak is much lower in intensity, but still there at 662, and we get a significant contribution from background. And when we attempt to back project those events, because they are not true events, those add just a baseline level of noise to our image. What's very nice about this imaging system, though, is that even with this contribution of noise, because it is not actually correlated with anything, we still do isolate our source, which we can see at 0, 0. So I realize that was a lot to go through. Thank you all very much, and I'd be very happy to take any questions you might have. Yes. From PB, do you mean that the plutonium beryllium source is emitting americium? Yes, there was americium in the plutonium beryllium source. So they were specifically looking at detecting the 60 keV line from americium that was present in the source. Of course. All right, I'll hang out for a couple minutes. If anyone has any questions, please feel free to enter them into the chat. If not, thank you all very much for your time. Question from Stephanie. Can you make an equivalent system for photons, or would it be impractically large? So the system that I just showed here, this was for photons. This could be used for neutrons in that we can look at neutron double scatter events between the still beam interactions as well. But this setup was specifically used for photons, which is why, and oh, yep, oh, I had it backwards. All good. Thank you very much. Oh, so could a system like this be used for neutrons? So in this case, the inorganics, the LISO, are not sensitive to the neutron interactions in that we can't differentiate them in interactions. So they would not be useful, but we could absolutely use this system for the neutron imaging as well. However, it would suffer from the same lever arm effects in that we would have interesting angles to occur, and that would give us this distortion in the image. One way we could get around that, though, is just filling in the SciPM array with all still beam cubes, or some combination of still beam and inorganic, or some organic and inorganic, and that would help alleviate that effect. But yes, a system like this could absolutely perform neutron imaging as well. This was just built to demonstrate gamma imaging and to ensure that things were being imaged and taken into account correctly. All right. With that, my contact information is in the bottom left. If you all have any more comments or questions for me, please feel free to email me. I'll hang out for just another couple more minutes if anyone else has any questions. But with that, thank you all very much.